Hi everyone, and welcome to Mike Likes Robots. This video is a second part to the QuickStart guide of getting a Jetbot up and moving using ROS2. I'll link that video at the top, but this video is a deeper dive into how to format the SD card, how to set up Docker using VS Code, and how to write the launch files and even some of the code for how to move the robot around. So really dig into how ROS2 works and how to write code for it. First, let's start with expanding the SD card partition. This SD card issue only seems to affect 4 gig models, and it's due to how the SD card was flashed. The SD card main partition is only 24 gigabytes big, no matter the size of the card. My card is 256 gig. We can see this when I run the df/ command to look at disk usage. If we look, the card is 94% used, and I haven't added any files to it yet. Thankfully, there's an easy way to fix this issue if you encounter it. Just change directory into jetcard/scripts, then do a git pull to update that directory. This updated the resize script, which I'll run as sudo and then reboot. Once this is complete, we can run df/ again and see that the usage is down to 10%. Now we can start adding our software. Next, we want to make sure Docker is working on board, as we're using it to build a container with our software and dependencies. We can test it by trying to run hello world. When we run this, it fails, but it's due to a permission error. That means it's installed, but our user doesn't have permission to use it. We can add the user to the Docker user group by doing sudo usermod -ag docker $user, then reloading the terminal. I'm going to reboot as it's fairly quick to do. Now we're back online, we can run hello world. And this time it pulls and runs the hello world container. We have all the permissions we need. Our next step is to clone the code. I'll provide the link in the description. We can just do a git clone and paste the URL. Then we'll change directory into the folder, and we can see 2 workspaces, complete and incomplete. The incomplete workspace is what we're going to be using, and we're going to bring it up to par with the complete workspace. If you want to just get up and running, as in the QuickStart video, use the complete workspace instead. Our next step is to make sure the extensions we need are installed in VS Code. We'll make sure the remote SSH extension is installed, then search for dev containers and make sure that's installed as well. Once they're installed, we can connect to the Jetbot. Now that we're connected to the Jetbot, we want to open the folder of the incomplete workspace. Ctrl-KO will open a folder. We can navigate to the folder and click OK to open it. Next, we want to start building the dev container for all of our dependencies. We can use Ctrl-Shift-P to open the menu, then search for Open Folder in Container. Click OK in the current folder. As there's no container configured yet, VS Code will give us a list of options that we can use. I'll use Alpine to show the container opening. We'll be building our own container to replace it soon. Latest version is fine. You can optionally install features, but I'll skip this step. This process creates the .dev container folder with config files for the container. Now the folder is open inside a Docker container running on the Jetson, accessed over SSH, all in VS Code, which lets me edit code as if I'm editing locally. We can take a look at the config file that it's built. It's called Alpine and is based on a known Docker file from Microsoft. This file is where we can add the run arguments, like the volumes to mount in the container, and which VS Code extensions should be run inside the container. However, Alpine isn't what we want. We want our own ROS2 container, which isn't available in the standard list. We can change the image line to look for a Docker file locally, then create that Docker file and start to build our container. I'm going to paste in a template file I found before. I've lost the source and I'd love to give credit to its author, so please comment if you know its source. The first thing to note is that the base image is humble, which is our flavor of ROS2. From there, it creates a new user called VS Code. This is a Docker best practice to create a non-root user, but give them sudo privileges. We're going to customize this by changing the username to Jetbot. User$username will be replaced by user Jetbot, and that means the container will run as the Jetbot user by default. This user mod command adds our Jetbot user to the video group, which gives us webcam access. The next lines are standard for updating the system. Then we do a ROS-dep update to install any missing ROS dependencies and add a line to the bash RC to source ROS2. This is what gives us access to ROS2 build tools out of the box when we run the container. That's our Docker file complete for now. Back in the config file, we want to change the name to ROS2 humble, then paste some lines in that we need for this container. These runargs run as privileged, giving us access to all devices on the host. We run with the host network as well. We mount the current workspace into the container. This mount is to make sure that bash history is available. Now we'll attempt to run inside this container. Pull the menu up and click Rebuild Container, then wait for the build to finish. If you have an issue building the container, like I am here, try clicking Edit in SSH. It will pull up a log file showing what happened. In this case, a user called apt wasn't allowed to do an apt update. This is an error from my system being out of date and can be fixed by doing an apt update and apt upgrade. And this time around, the container is successfully built. Now if we open up a terminal, we should have full access to ROS2 commands. And we should be able to build our workspace as it is. And our package built successfully. So now let's take a look at the source code. This was generated using the ROS2 tools to create an empty package and then had some details filled out and the source code written and tested. Most of the important code in here are in the motor controller and motor.py classes, which both come from the Jetbot Git repository, which I'll link in the description. These files I've taken from that repository and adapted them, just taken out code that isn't needed. So for example, traitlets are in there, which aren't needed for this. It's been stripped down to the bare essentials to make the code work. So feel free to take a look at how this works and the motor.py class as well. But that's not the target of this video. Here we're trying to make it work. So one thing we can do here is run the teleop twist keyboard node. What that will do is produce messages based on keyboard input. Let's run that node and take a look at what topics it produces. Now the package isn't found because we actually have to install it on top of the base image. So the way that we can do that is open up our Docker file, and then instead of just git, we can also add ROS humble teleop twist keyboard. Now this will ask us if we want to rebuild the image, but we can just save some time by installing it directly. Once that's finished installing, we can try running it again. We can see it opens up this menu. So the keys we're interested in are the U, I, O, JKL, M, dot keys. The easiest thing to do is just to use I to move forward, K to stop, and JL to turn left and right. So to see what it's doing, we'll open up another terminal. By doing a ROS2 topic list, we can see all of the topics that are available. And the one we're interested in right now is this command vel topic. There's two other topics. If anything happens to parameters and any log events that happen on rosout. But command vel is the one created by this teleop twist keyboard topic. So if we echo it, what this will do is print out any message that's sent on that topic. what we're effectively doing is using the command line tool to subscribe to the topic and just print out what it says. Now if we go back to the keyboard node and press I, we can see it set the X speed to 0.5. If we press the comma to go backwards, it sets the X to minus 0.5. With J, our forward speed is 0 and our angular Z is positive 1, meaning turn left. And if we press L, our angular Z is minus 1, meaning turn right. We can also press the other keys to see some other combinations that are available. And pressing K will stop it. So this command is the one that we need to listen to in whatever ROS2 node we've got that's trying to command the motors. So let's take a look at how that works. Main.py will create this Jetbot controller class. Inside Jetbot controller, we try to import motor controller, and if unable to, we use fake controller, and that just prints out that we're trying to move. And the point of that is that if you're not running on the Jetbot and you don't have access to the I2C Bus, which is needed to command the motors to move, then at least you can still see it working. So just on your local PC, you can still run it and see that it's doing something. We can see with the motor controller in the Jetbot controller that what we're doing is creating a subscription to the command vel topic and creating the motor controller instance so that we can actually issue commands. Now this callback function is called whenever there's a new message on command vel, like we've seen coming up here. In the case that happens, we calculate what our left and right motor speeds need to be and then set those in the controller. That's really all the translation layer we need to have a very simple translation between command vel and motors moving. Now we also want to set up our Gamepad. So on top of having keyboard as an available node, we also want to install teleop twist joy. So let's add that as well. And we need one more node to be able to convert from our generic joystick, as in our PS4 controller, to the joystick topic that we need from Linux. We need this extra topic. So we need to be able to run 3 nodes at once. Again, I'll install them directly in the container. Now that installation is complete, we can run our nodes. So we need to run the Joy Linux node first of all. Our ROS2 run here takes a package name and an executable name. So when we run this and connect to our controller, this node will take the input from our controller and write messages to the Joy topic. So if we do a topic list, we can see the /joy topic. And if we echo /joy and then move the joysticks around, we can see these axes are changing with the joystick moving around. We can also press buttons and see that it's coming up on our message. So we have full Gamepad input through this node. Next, we want to take those messages appearing on the Joy topic and output them into the command vel topic. We could translate this ourselves, but the twist joy package will do that for us. So we can do a ROS2 run. And then when we run this teleop node, we can again do ROS2 topic list. We can see our command vel topic. And when we echo that, we can see nothing coming through. And that's because this teleop twist joy node has our enable button as 5. But if we echo the joy topic again, the button we want is 5, which is 0, 1, 2, 3, 4, 5. This button here. So if we press all the buttons on the gamepad, none of them turn that 0 to a 1, which means that we can't press our enable button. We have to remap it. There's a couple of ways. The first is that we can pass it here using our ROS args. and if we set it to 0, that should be our A button. Yeah, 0 is our A button. So we want to set that to 0, and then if we run that, our teleop enable button is set to 0. Now if we echo command vel and we press the A button, it starts transmitting messages on command vel. So we're able to now move the robot, but the axes aren't mapped correctly. We need to remap the correct axes for the joysticks. An easier way to play with this instead of typing out different parameters each time is to start to use a launch file. So that's what we're going to do next, is create a joystick launch file. We want to create a launch folder within Pi Jetbot control. We can specify launch files in a few different ways. Specifying it in Python is a particularly good way to have dynamic launch files, but for simplicity, I'm just going to write it in YAML. So joy.yaml, and then we need to specify that there's a launch. One of the things that we're going to launch is a node. The node will contain the package of Joy Linux and the executable of Joy Linux node. Our next node that we want to execute is the teleop twist joy. So we can use package teleop twist joy. Our executable is teleop node. And here's where we can pass our parameters in. And here's where we can pass our parameters in. We need to provide a list with the name of the argument that we want to remap. So first we want to use enable button, and then the value that it will be remapped to, so 0. Now when we launch this launch file, we'll get the same as the two terminals that we had on the left. So we should be able to do ROS2 launch Pi Jetbot control joy.yaml. Now there's a couple more steps before this will work. First, we need to actually tell ROS2 to copy that launch file over. And we can do that in setup.py. So we've imported glob, and what we can do is in this data files listing, we can add another one. Share plus package name, and then we're going to glob any files in the launch directory. Now if we do a colcon build with symlink install, symlink install means that we can edit our Python source code where it is and then run it without having to rebuild. Unfortunately, that doesn't seem to work with YAML launch files. So the symlink install isn't doing anything for us here, but it's a habit that I've built. Let's change that to launch ***. And that has copied our file now. Now if we run that launch file that we tried to launch before, we need to source the local environment. So that's source install setup.bash. Now when we launch the launch file, it will launch the two nodes that we specified, and it will use the arguments that we've given it. So the enable button is on button 0. Now we can see if we press the enable button, our Angular is already correct, and our linear isn't being produced at all. So now we want to remap our linear axis to be the correct one. So we're going to go back into that launch file. We're going to create a new parameter. The name will be linear axis, and this is actually 3 different options within linear axis for x, y, and z. So we're going to specify .x, and the value will be 1. And we can see that by, again, echoing the joy node and seeing what the left analog stick forward and back axis is. And that's index 1. So let's shut this down. We need to rebuild, but we don't need to resource. And once this is complete, we can launch that file again. But it's still mapped to the same thing. Excuse me, that should be axis linear. So we need to rebuild that again. Now we can launch it again. And then hold down the enable button. And now we can see our linear X is starting to move with the left analog stick forward and back. The angular Z is moving with our right analog stick left and right. So that's working exactly as we want. What we can do now is add to our launch file to launch our motor controller. But before we do that, it's easiest to check it runs by itself. Let's do a ROS2 run pi. First we need to source the workspace within this terminal. And then we can ROS2 run pi jetbot control jetbot. If we can run this successfully, which we can't because we don't have the module named Adafruit, once that's able to run successfully, we can put it into our launch file. So let's make that work. The package it's missing is Adafruit motorhat, so we can pip3 install that, and pip3 isn't available. So we can install it with apt install -y python3 pip. Now, as this is working, we can build up our Docker file to include these dependencies. So we can add python3 pip to our list of app dependencies, and we can start to install our Python dependencies. So it's Adafruit motorhat, then we can save this Docker file. Now our Docker image will again match what our current container is running. So we're keeping track of our dependencies as we go. Let's try and run our Jetbot again. And this time we can't find a module called Quick. Now you would think pip3 install Quick would get it, but it's actually called sparkfun Quick. Now we'll try running again. And we can't find a module named serial. So our last dependency to install is pyserial. Okay, now all our dependencies are installed, but we have this new error, which is permission denied I2C1. Now we showed in the dev container that we are privileged and with network host, which means we should be able to access that dev device if we're root. But we're not root, we're a user, and that user doesn't have permission to access it. We can see that if we lsal dev I2C star. Here we can see that all of the I2C devices exist, but they're owned by a group with ID 108. Unfortunately, our user is not part of that group. Now, to show you how to fix that, if we go back into our terminal that's directly connected and then execute the same command, this is outside the Docker container, and we can see that it's owned by the I2C group. So essentially, on the host system, a user group called I2C owns these devices, and inside the Docker container, group 108 owns the devices. So what we're going to do to fix this is to change our Docker file to create the group ID with 108 called I2C, and then add our user to it. We can add this code, which adds a group with ID 108 called I2C, and it adds our username to that group. Now, if we rebuild with this Docker file, we should be able to access the I2C bus. Now that we're back in, we should be able to, again, source our install setup.bash and then try to run our node. and our controller started up with no errors. So let's add it into our launch file. Our package name is Jetbot control, and the executable is Jetbot. And that's it. We can rebuild, we can source, and we can launch. Now when we connect the controller, press the enable button, we're starting to get messages appear that are being sent to the robot. And that's it for bringing our incomplete workspace up to par with our complete workspace. If you want to see the robot moving around, please see the video linked at the top. It will show the QuickStart guide, and it will actually show the robot moving with both the keyboard and the gamepad. So in this video, we saw how to set up in depth the Jetbot with ROS2 in a Docker container running through VS Code. We also saw how to create a ROS2 launch file and saw how to debug some of those messages passing through topics. In the future, we'll continue using Docker to run code. It's a great way to encapsulate dependencies all in the same place so that you can just give someone the file and let them use your software. So with that, thanks for watching, and I'll see you in the next one.